In a modern AAA game, the biggest challenge isn't always the stunning graphics or the complex AI. Nope, it's making all of that stuff work together seamlessly without a single stutter. So today, we're going to pull back the curtain on the architectural secrets that let a high-performance engine manage thousands of tasks in perfect harmony, all within a fraction of a second. Let's dive in.
Here it is, 16.67 milliseconds. That is the entire time budget you get for a single frame if you want your game to run at a silky smooth 60 frames per second. That's it, not 1 microsecond more.
Think about it. Everything has to cram into that tiny little window. Graphics, AI, physics, you name it. If your main thread tries to do all of that one by one, sequentially, you create a massive bottleneck. The game stutters, the frame rate tanks, and the whole illusion is just broken. The simple truth is, you just can't do it all in a single file line. It's impossible.
So this brings engineers to a really fundamental choice. Do you go with a synchronous or blocking approach, where the main thread literally stops and waits for a heavy task to finish? Or do you use an asynchronous, non-blocking model, where you can fire off that heavy work to run in the background while the main thread keeps things moving? For a modern engine, well, there's really only one right answer.
To beat that 16 millisecond clock, the entire engine has to be built from the ground up to orchestrate work asynchronously. See, it's not just about doing things fast, it's about doing many things at the exact same time without them tripping all over each other.
All right, so the very first step in this grand orchestration is creating a super clean handoff for all that heavy lifting. And this is where a really powerful pattern comes into play: the event-to-job pipeline.
Let's take an example. Imagine a physics collision in the game. We can think of that as an event. Now, instead of the main thread grinding to a halt to process all the complex consequences right then and there, it uses a function, let's call it dispatch async, to instantly create a job and hand it off to a background worker thread. Just like that, the main thread is free. It keeps the game responsive while all the heavy number crunching happens somewhere else.
And this handoff is just incredibly efficient. I mean, look at these numbers. The call itself is non-blocking and takes less than 100 microseconds. That is a tiny fraction of our 16 millisecond budget. It adds practically no memory overhead, and most importantly, it's designed from the start to be completely thread-safe. This right here, this is the bedrock of a responsive system.
Okay, so we can offload a single task. That's great. But what about absolutely massive workloads, like updating the AI for thousands of characters all at once, right? If every thread just starts changing game data whenever it feels like it, you get pure chaos. This problem requires a much more structured pattern.
And the solution is this really strict three-step pattern called compute then apply. Here's how it works. First, the engine takes a snapshot of all the data it needs. Think of it like a photograph of the game state at that instant. Then, all the worker threads get to work on that snapshot data in parallel. Critically, they're all reading from the same initial state. Finally, once all that work is done, the results are applied back to the live game world in a stable, predictable order. This guarantees you get the exact same outcome every single time. This pattern gives us some incredible guarantees. You don't need complex things like locks or atomic operations where threads are basically fighting each other over data. Why? Because each job effectively owns its own little piece of the puzzle during that process phase. And this determinism, oh man, it is absolutely critical for debugging. It gets rid of those bizarre, impossible to reproduce bugs that drive developers crazy.
So we've dispatched thousands of jobs. They've all done their calculations. Now, how in the world do we get all those results back to the main loop without causing a massive data traffic jam? I mean, if we just block the main thread to wait for each result, we've defeated the whole purpose of doing this asynchronously. This is where we need a really high-speed, specialized data structure. This table kind of shows the trade-offs. We have many worker threads producing results, so a single producer queue just won't cut it. But we only have one main loop consuming all those results, and that's why the multi-producer single consumer, or MPSC queue, is the absolute sweet spot. It's designed for exactly this kind of scenario. The MPSC ring buffer is the perfect tool for the job. You have lots of worker threads, the multi-producers, all pushing their finished results into the queue at the same time without blocking each other. Then, our single consumer, the main loop, can come along and drain all of those results in one super efficient batch operation. It's the ideal way to aggregate a ton of work from all over the system. So, let's put it all together.
When you combine these powerful patterns, the engine moves from a state of potential chaos to one of finely tuned asynchronous harmony. It's really quite beautiful.
And here's the result you get. You can see how that 16.67 milliseconds is carefully partitioned. Dispatching all the events and jobs takes less than a millisecond. All that heavy parallel processing gets done in under 5. And this leaves a really healthy budget for rendering and anything else we need to do, with even a little headroom to spare. It's a well-oiled machine.
And the real payoff? Over 90% CPU utilization. Now what that means is the engine is wringing almost every single drop of performance out of the hardware. No CPU cores are just sitting around idle, no processing power is being wasted, everything is put to work.
So in the end, these aren't just isolated little tricks. They are the architectural pillars that hold the whole thing up. The event-to-job pipeline decouples all the systems, the compute-then-apply pattern unlocks massive but safe parallelism, and those MPSC queues provide that high-speed, non-blocking off-ramp for all the data to get back home. It all works together.
Which really leaves us with one final exciting thought. With all these technical constraints solved, with the main thread now free to be a conductor instead of a laborer, and with every CPU core pulling its weight in perfect harmony, what does that unlock creatively? What kind of living, breathing, incredibly complex worlds can now be built? That's the real question.